All right, so literal equations. Equations that have two more variables. Like a squared plus b squared equals c squared. You guys remember that? Pythagorean theorem. Okay, that's a literal equation. Usually they tell you what a and b are, and you can find c. Or they tell you a and c, and you can find b. Every formula you've come across throughout all of 7th grade, 8th grade, 6th grade, like perimeter areas, those formulas are literal equations. Okay. An example that maybe we're really accustomed to, that we use a lot, is distance equals rate times time. Okay. Distance equals rate times time. Now we usually, obviously, abbreviate that and go d is equal to RT. You guys used that before? Distance equals RT. Okay. What I want to do here is I want to go through a couple questions here that kind of express the need for understanding literal equations. Okay. Most of the time, you guys, when you're working with formulas, you identify what formula you're going to need. Okay. So this question here says, if you traveled 240 miles and the drive took you 4.5 hours, can you determine the average rate or speed that you drove? So what you need to be able to do is kind of search through your catalog of formulas that you know and see which ones relate distance, time, and rates. Okay? And that should generate distance equals rate times time. So we choose that formula. Okay? Distance equals rate times time. And now what we're going to do is we're going to go through and figure out, okay, well, what was the distance they talked about? Well, distance was 240 miles, right? So plug that in there. And so it's just that substitution game that we've played before. 4.5 hours, is that a rate or a time? Time. And then it's asking us for the average rate, or a lot of times you'll see them write speed that you drove, so that's your rate, right? So then you just plug those things in. So I'm looking at distance is 240 is equal to rate is what I'm looking for, and time is 4.5. So now if I write RT, can I write it as TR? So that's why I'm putting 4.5 first, and then my rate second. So you see that 4.5 is a coefficient for your rate, right? Now how I solve for rate? You divide. Okay. So divide by 4.5, divide by 4.5, and if you do that, I'll save you the struggles of getting your calculator out. It's 53.33 repeating. Okay, now I got to talk about a unit here, and this is going to be important for us as we move throughout the year. I think there's little things that a lot of times we neglect or we don't pay attention to, and we can maybe survive or keep our head above water by doing that. But what you're going to find out is in a year or 2 years or 3 years, when you're in another math course or science course and you neglect to pay attention to units, you're going to fall very far behind in those courses, because your science teachers especially take the understanding that you do this in math and you use this often in math, that they don't need to teach it, and they won't teach it. And the idea is we have to remember that this 240 had a unit with it, didn't it? It had miles with it. Okay. When I look at the 4.5, the 4.5 had hours with it, right? Times my T, times my R, my rate. Okay. So when I divided by 4.5, what I really divided by was 4.5 hours, right? Does that make sense to everybody? So when I come over here, I divide by 4.5 hours, and it gives me, the ability to write it this way. So I do the division with the numerical parts, but now I'm going to do division with the unit part, and I get miles divided by hour. And you guys might have seen this written this way, miles divided by hour as your unit, or what are you guys more accustomed to? MPH. Where the P stands in for the word per, but it's referring to the fact that we're going 53.33 miles per, or for every 1 hour. Does that make sense? Okay. Being able to understand that process of developing the units is going to be very important for us. There's an entire section. I believe it's the next section. Just want to double check real quick. What's the name of that unit? Ratios. Yep. The next section will actually talk about, it will be fully dedicated to making sure we can do the algebra with units. Okay. The next one says if you traveled 240 miles and you drove an average speed of 65 miles per hour, can you find the time it took to complete the trip? So now, it's still distance equals rate times time, but now it says can you find the time? Can you find the time? So that is what we're going to be focusing our attention to. The time is what we're going to be solving for. Okay, so that means that the distance and the rate must be things that we can pull off of the problem or out of the description. Stop it. So 240 would be the distance. And now I'm going to write miles here. 240 miles, right? The rate is 65 mph. I'm going to write it this way. Miles per 1 hour. Okay, and I'm going to try to find the time. Okay, most of the time I think people are going to do this. They're going to write, and this is fine, 240 is equal to 65t. Would you guys agree with that? What are you going to do to both sides there? Divide by 65. And you're going to get, I think, approximately, like, was it 3.7-ish? Okay. Now, we got to determine, well, is that hours? Is it miles per hour? Is it miles? What's the unit left over? Well, we saw it for t, right? So we know that stands for time, so we probably shouldn't put miles. But I want to talk about the approach here using this logic. 240 miles was equal to 65 miles per hour times t, right? Now, you guys are perfectly fine by or dividing by 65. But what if we talked about the same as dividing is multiplying by the what? Reciprocal. So if I multiply this thing, I should give myself a little bit more room here. One of these buttons are working. It does this about every 50 minutes. There we go. So you take and multiply by the reciprocal. So 1 over 65, right? But when I multiply by the reciprocal, I'm also using the units. So the reciprocal of the units would be hours and miles there. Does that make sense? Now, does that hour cancel with that hour? That mile with that mile, right? This 65 with that 65. So all I'm left with is t. But now over here, we multiply by 1 hour over 65 miles. So let's think about this. Let's think about this. If I've got this 1 hour over 65 miles, 240 miles over 1, straight across, okay, you get hours and miles, right? Across the bottom, you get miles and nothing, correct? What's going to happen with that miles and that miles? Cancel out, okay? And what is the only unit you're left with? Hours. So that's where I get the 3.7 hours as my time. Being able to do that algebra with the units is important. Thank you, Charles, for being so respectful.
Yeah.
What's up?
My homework's on math or web design.
I don't care.
Well, I don't care.
I'll get it up. I'll get it up, Chuck. Shut up, Chuck. All right, so he's not the prisoner, is he? All right, here we go. We got the equation here. It says the equation 10p plus 5s equals 80. Okay? And you're going to see a lot of equations like this, so I went ahead and I described what the P and the S stand for. P stands for pizzas, number of pizzas that we're going to be able to buy here. S stands for the number of sandwiches that we're going to buy here. But the coefficients, 10 and 5, represent the cost of pizza and cost of a sandwich. Okay? Lacey, please turn around. So we have our cost of a pizza, our cost of a sandwich, and it's going to equal 80. So what's that 80 represent? So if I've got the cost of a pizza, or cost of how much money I'm going to spend on pizzas, plus the cost of how much I'm going to spend on sandwiches, so that the 80 says that I'm going to spend a total of 80 bucks. Okay? Maybe that's all I've got allocated for whatever I'm buying this food for. Okay? So I want to go through some examples here of how we have so far in this course dealt with a situation like this. And they asked me, if you purchased 3 pizzas, how many sandwiches could you buy? Well, if I start with my original equation here, it says 10p plus 5s equals 80, and they're in this first situation saying pizzas is 3, right? So does that make sense that I could take this p and rewrite it as 3? So now I have 10 times 3 plus 5s equals 80, right? What's that 10 times 3 turn into? 30. So 30 plus 5s's is equal to 80. Now what would you do to both sides? Try to find s. Subtract what? Alright, that's what I'm solving for first, right? Subtract 30. So you get 5s is equal to 50. So then what? Divide by 5, and s would be 10. Okay? So, if I start with 3 pizzas, if I know I have to buy 3 pizzas, that then allows me to eventually buy 10 sandwiches with it, right? With my 80 bucks. Now the question is, well, what if I had 6 pizzas? Okay, and as we do this process, I want you to think about what we're doing and how that kind of compares to what we did here in purple. If I now had 10 pizzas, I'm going to start with 10p plus 5s is equal to 80. I meant 6 pizzas. 6 pizzas. What am I going to replace p with? 6. So it's 10 times 6 plus 5s equals 80. Is that kind of the same thing we did right here? Okay, but using a different input, right? So it gives me 60 plus 5s is equal to 80, which is the same as that line right there, just a different constant. What are you going to do to both sides? Subtract 60, so I have 5s is equal to 20, and now what am I going to do next? Divide by 5, right? So s then is 4. Would you guys agree that as we did that, the process was the same? Okay, we substituted p, evaluated that, got 30 or 60. Then we subtracted 30 or 60 from both sides. Then we divided both sides by 5, right? It's the same thing. So if I ask you, well, what if I'm going to do 7 pizzas? Would you do the same kind of substitution and solving for that variable? Okay, so that's what we worked on in section 2.2, 2.3, 2.4, being able to solve those equations once we substitute. It says, can we write the same results before substituting? Or can we arrive at the same results before substituting? And the answer to that should be yes. Okay? And this is the purpose of literal equations. I don't want to do this. If I want to know, how many sandwiches can I buy when I buy no pizzas? How many can I buy when I buy 1 pizza, 2 pizzas, 3 pizzas, 4 pizzas, 5 pizzas, 6 pizzas, 7 pizzas, or 8 pizzas? I don't, because there's 8 situations there. Okay? I don't want to have to solve an equation every single time that I want to figure out how many pizzas I have. Does that make sense? I don't want to do that process. We just went through 8 different times. There should be something that allows me to do it quicker. Okay? And that's what literal equations allow for. So what I'm going to start with is the 10p plus 5s equals 80. I start with my literal equation. It's got two variables, two or more variables. And now I want to work through essentially the same steps that we did above, but I'm going to skip the substitution part. Okay? So above, then we try to get this thing by itself. Try to get the s by itself. And first to do that, I got to get the 5s by itself. So what am I going to do? Up here, we subtracted 30 or 60, right? Well, that is the 10p, is it not? So I subtract 10p from the left. It's going to go away. Now, over here, I got to subtract 10p. Now, over here, I don't know what that 10p stands for. It could be 0 if I have 0 pizzas. It could be 10 if I have 1 pizza. It could be 20 if I have 2 pizzas. That make sense? So I can't merge it with anything. It's not a like term with that 80. So what we do is we write down 80 minus 10p. Okay? We basically tell ourselves, or whoever's reading our work, that yes, we do subtraction there, because we subtracted 10p from the left-hand side, so we have to subtract that from the right-hand side, but we really aren't going to do the subtraction. Does that make sense? Did I subtract anything? Did I actually physically say, start with this amount, and what do you get when you remove this amount? Or do we just write 80 minus 10p, right? But we didn't logically figure out what that difference was. Does that make sense, everybody? Above, we were getting like 50, or getting 20. So we took 80 minus 30, or 80 minus 60. Here, we don't know what we're minus. We don't know that 10p is variable. It's changing. So we just write it as 80 minus 10p. Now, just like up here, you then divide it by 5 to both sides, right? So I'm going to do that. I'm going to take that and divide by 5. So it's going to leave me s on the left. Now, when I divide the right-hand side by 5, you have to divide the entire right-hand side by 5. So what that turns into is 80 over 5 minus 10p over 5. But that can be written a little bit better. What's 80 divided by 5? 16. And what's 10 divided by 5? 2, right? And it's a negative 2 in this case. And I get that formula. So what that formula does, guys, is that provides me, right there, that provides me with a method for finding out how many sandwiches I can buy when I know how many pizzas I've bought. And it's a lot more efficient, a lot quicker than the process that we laid out up here. So let's kind of do maybe a little T-chart here. If I put P here for pizzas and S here for sandwiches, I'm going to say, okay, if I go 0 pizzas, 1 pizza, 2 pizzas, 3, going to finish over here, 4, 5, 6, 7, and 8. Now, I know I can't go above 8 because then 10 times 8 would be 80, right? So if I go 9 times 10, it would be 90. Well, I don't have $90 to spend, right? I only got $80 to spend. But let's try it. If I chose 0 pizzas, think about this. It's so much easier to use this thing here. If I had 0 pizzas, this would be 16 minus 2 times 0. What's that give me for S? Gives me 16, doesn't it? So if I buy 0 pizzas, I can buy 16 sandwiches. Well, let's try it with 1. Well, if S equals 16 minus 2 times P, but P is now 1, what's 16 minus 2? 14. Let's try it with 2 pizzas. So 16 minus 2 times 2, so you're right, it's 12. 3 pizzas would be 10. Does that match up to what we found earlier? But right now we've got 4 answers in the time that it took us to find that one answer there, don't we? 4 pizzas. Be 16 minus 8, right? So 8 sandwiches. 5 would be 6. 6 would be 4, 2, and then 0. I think you can start to see a pattern, right? As these are increasing by 1, what are the sandwiches doing? Decreasing by 2. Okay, so you can, once you recognize that pattern, you can assume that it exists forever there. But do you see it? The purpose of a literal equation is for us to generate that data much quicker than solving the individual equations 8 times. Okay. Let's look at this one. It says if there's 4 things here, but it's really all the same question. It says if ax plus b equals c, can we solve for x? If ax plus b equals c, can you solve for x? What I want us to get in the kind of the mode of here is recognizing that I want to solve for x. So then I'm going to go find the term that x is in. And I'm going to highlight the whole term. And I'm just going to leave it alone. I'm not going to do anything until I get it by itself. And that's what we got to think about. How can I get that by itself? So it's with a plus b, right? How do I get rid of that plus b? Subtract it, right? So I'm going to minus b from the left, and I'll minus b from the right. So ax equals, now I don't know what c is. I don't know how much c is. And I don't know how much b is. So can I physically do that subtraction? No. Okay? But I can tell the people reading my work that when I do know what c is and when I do know what b is, I will be subtracting them. So c minus b. Is it okay? Now I've isolated the ax, right? And I want to solve for x. I want to solve for x. So how are these two stuck together? Multiplication. How do you undo multiplication? Divide. So divide by a. And that's going to leave me just x. Come over here. And remember, you have to divide the entire side by a, right? So the easiest thing is just to write one large fraction bar and just left with then c minus b over a. C minus b over a. Or some people like to do this. So when I write it this way, it means I'm dividing the c by a and I'm dividing the b by a. Either one of those is fine. All right, now and this is something that you're going to hear me talk about all year long. We should be able to have a technique for checking ourselves, right? Here's the technique. Start with the original equation. And that c right there, I'm going to just let it be c, and I'm going to choose random values for a, x, and b, and see what I get with c. Does that make sense? Okay. Now, when you're doing this, my suggestion to you, you can use any numbers that you want. But using 0 sometimes can confuse people, okay? So stay away from 0. If you don't need to use negative numbers, we probably don't want to use negative numbers, right? If you don't need to use fractions, we probably don't want to use fractions. So my suggestion is use your whole numbers, okay? Or better yet, use your natural numbers. Stay away from 0. I would also stay away from 1 because you're not going to be able to always gain the right conclusions. But what I do is I say, okay, well, I'm going to let a equal, give me a number. I heard 7. Let b equal something. What do you want b to be? 6. And what do you want x to be? Okay. So 7, 6, and 5. 7, 6, and 5. And I'm going to plug those in and see what that gives me for c. So what's a times x? What's 7 times 5? 35. Okay. Plus then b, so 35 plus 6 would be 41. So we got c here to be 41. Does that make sense to everybody? Okay, and that's just by plugging those random values in there. Okay. Now what I'm going to do is I'm going to take this thing here. And it's actually that thing. And I'm going to plug these values in that I know, and hopefully I get x back. So what's c minus b? Well, c we chose was 41, right? Minus b was 6. All over a, which we said was 7. What's 41 minus 6? 35. Divided by 7 is 5. Is that the x that we had? Does that make sense to everybody? So that can be the check That can be the check to make sure that you have solved the literal equation correctly. All right? There's some parts to that, ideas that we have to stay away from 0, stay away from 1, okay? And then choose variables for the side that is not isolated. Okay, so C here would be isolated. Choose variables for these things, or amounts for those things, and then substitute. Let's do the next one. Can we take that thing and solve for A? So I'm going to solve this one for A. Again, I need to get that by itself, right? So what do I need to remove from both sides? Lindsay? B. So subtract B. Subtract B. So we get AX is equal to C minus B, right? Now I'm solving for A. So what do I need to divide both sides by? Divide both sides by X. Cancels out. Divide by X. So this is going to generate A equals C minus B over X. Let's see if it checks out. What's C? Using these values, what was C? 41 minus B, which was 6. I'm going to divide by X in this case, which would be 5. So 41 minus 6 is 35. Divided by 5 is 7. Is 7. So 7 is pairing up with that A, right? Is that what we had up there? Yeah. So we know we've done it correctly. Okay. What about this next one? This next one should be a little bit simpler. I want to solve for B now. So what is on the same side as B? A and X. How are they stuck to B? How are they stuck to B? They're added to B, right? So to unstick them from B, I need to subtract them. And what's that going to give me on the left? Just B, right? On the right, I got C minus AX. And I'm going to allow you to check that on your own, but if you check that out with those values that we chose or any other random values, you're going to see that you do generate the correct B term when you play that little checking game. Is that all right? The last one says AX plus B equals C. Can you solve for C? What would be the first step there? You want to solve for C, right? So this phrase, whenever they ask you solve for a variable, what that means to us, okay, you might want to write this down. We're going to see this over and over and over throughout the rest of the year. Solve for a variable means isolate that variable and make its coefficient one. So let's think about this. I'm trying to solve for C, right? Look at where C is. Is it isolated? Is it by itself? Yeah. Has it got a variable or a coefficient of 1? Yeah. So it's already done, right? Okay. And so isolate the variable and make its coefficient 1. But you're going to hear me say that this variable is already solved for. So in this case, C is already solved for. It's already isolated with a coefficient of 1. Eventually, and I think it's chapter 4 maybe, we're going to start graphing things. We're going to graph lines, okay? And lines use, in their equations, x's and y's. So there'll be times where we want to isolate the y and get it all by itself with a coefficient of 1. There'll be times when we want to isolate the x and get it all by itself with a coefficient of 1. Does that make sense? You're going to hear me say that phrase. In preparation for just a practice of some more literal equations and to work inside your homework likes to use a combination of formulas that you already know and then just some random thing. You look at the bottom of that page, I just got some random things there, right? I just took some numbers and letters and plugged them together with pluses, minus, multiplication, division. But in your homework, they might say, take the perimeter of a rectangle and solve for the length, okay? So we got to have some knowledge of some common formulas, okay? A formula is an equation that states a relationship among quantities. Okay? That relationship is going to be identified by multiplication, division, addition, and subtraction, your operations. Okay? Formulas are special types of literal equations. And the fact that they are kind of rules or tools that provide a shortcut process for identifying a commonly desired quantity. So go back to the one we've already did, distance traveled. Distance is equal to rate times time, right? That's what we talked about. Distance is equal to rate times time. Now, what that means to us is that the relationship amongst distance is the same as the relationship, that quantity is equal to the relationship of multiplication between rate and time. Okay? It's solved this way, or it's written this way, because the most common thing we're interested when we relate distance, rate, and time is to find how far we've traveled. Does that make sense? Okay? Most textbooks are going to say distance equals rate times time. But what I want you guys to understand is that if you learn that one, you should, with your algebra processes, you should actually learn 3. Can I divide both sides by r? If you divide both sides by r, what happens over here? Those cancel, right? And you get distance divided by r, or your rate, is equal to time. Does that make sense? Can I go back to that original one? And can I, instead of dividing by r, what could I divide both sides by? T. And those cancel to 1. And it leaves me distance divided by time is equal to my rate. So when they give us one equation, or one formula, in this case, they're actually giving us 3, correct? Does that make sense? And the idea is, would you rather memorize 3 things or 1 thing? You'd rather memorize 1. And we also together have our understanding of algebra that would allow us to generate those other ones when they're needed. Well, here's the idea. Why do they write it as distance equals rate times time in a textbook instead of time equals distance divided by rate? Instead of rate equals distance divided by time. The reason they write it as distance equals rate times time is because we are most of the time interested in distances, in finding a distance. Does that make sense? When we go a squared plus b squared equals c squared. The reason it's written that way is because most of the time we're looking for c, which was the hypotenuse's length. Okay? If I go up to, the perimeter of a rectangle, you guys know what the perimeter of a rectangle is? No?
We add all the time.
Okay, add all the sides. So you would have perimeter is a length plus a length plus a width plus a width, right? What's a better way of writing it? How many L's you got?
L squared plus...
Careful. Are you multiplying L's or are you adding L's?
Oh. I don't know.
Well, what's that say?
L plus L.
L plus L. So that is written as 2L, right? And W plus W is 2W. That's the way that we write that formula for the perimeter of a rectangle, right? 2 lengths plus 2 W's. Irrefutable. Nobody can argue that. Okay? However, that is also a formula that I could do this. Can I take and subtract 2 W's from both sides and get 2 L's? Divide both sides by 2. And now I've got a formula. You don't necessarily need to write this down because you're never going to use this. But now I have a formula for finding the length if I know what the perimeter and widths are. Does that make sense? So you've got inside that one formula, P equals 2L plus 2W, you've got other formulas if we go through our algebra and solve for those variables. Now, here's the thought. Why is it written this way, P equals 2L plus 2W? What are we most interested in usually when we're dealing with rectangles? We're interested in the perimeter. We're not interested in what the individual lengths are or what the individual widths are. We want the total perimeter. What's the circumference of the circle? You guys know that formula?
Pi d squared.
Okay. Pi d, I agree with that.
Oh.
Okay.
Is it that?
That is that.
Okay.
Okay, but d stands for your diameter, right?
Oh.
So, and I know that you learned that in middle school.
It's 2 pi r.
But I'm going to use 2 pi r, because 2r is the same as your diameter, right? I'm going to use that because beyond 8th grade math, you never see pi d again. And you're going to use in other math courses 2 pi r because it's more convenient, okay? I'm not going to explain why, but 2 pi r is better, okay? But does that give me a way to solve for r? If I divided both sides by 2 pi, does that give me r? So I got a formula to find the radius of a circle if I know its circumference, okay? It actually gives me a way, if we do use circumference is equal to pi d, if I divide both sides by d, what's it leave me with? Divide that by d, divide that by d, isn't it leave me with just pi? Yeah. Okay, so what does that say? That is actually the definition of what the number pi is. Okay, 3.14129, whatever. Okay, it is, you take a circumference of any circle, no matter how big your circle is, and you take its diameter, no matter what the diameter is. When you divide them, they'll always give you back 3.14 on forever. Okay, so that's the definition of pi for us. What's the area of a rectangle? Length times width, right? Maybe you've seen it as BH, base times height, length times width, same thing. Area of a triangle?
My R. Oh, 1/2.
Close. 1/2. My base times my height, which could be base and height could be referred to as, maybe you call the base the width, the height. I don't know if I call that a length, but what about area of a circle? Pi r squared. Okay. What about Celsius? Temperature. You know how to find Celsius as a temperature? That's Kelvin. Okay. So we've got. So the idea is that we're going to take, because here's the thing. This is the science aspect of it. 32 degrees Fahrenheit is what in regards to Celsius?
Fahrenheit.
How many degrees Celsius is 32 degrees Fahrenheit?
I don't know.
What is the freezing point in Celsius?
I don't know.
0.
Oh.
Okay? That's why I think most countries probably use Celsius over Fahrenheit, is because freezing is a very nice value of 0, right? It's kind of the breaking point of our number line, and then it's then that physical behavior. But for Fahrenheit, it's 32 degrees, right? Does that make sense? Okay. So now what we have to do is actually we multiply by 5/9. Okay. And that will allow, once you take your Fahrenheit, so if let's say it's 32 degrees Fahrenheit, subtract 32, you get 0, right? 0 times 5/9 is 0. So Celsius is 0 when Fahrenheit is 32. When, let's say Fahrenheit is 100. I go 100 minus 32, which would give me, 68? I take 68 and multiply it by 5/9. That will give me my Celsius temperature, which is going to be less than the Fahrenheit. Does that make sense? Okay. But that's how I find the temperature in Celsius. Now, why is it written that way? Because most scientific applications, most other countries use Celsius in favor of Fahrenheit. Does that make sense? Much like they use the metric system in favor of the English system that we use. All right. But all those formulas, guys, they're all written in terms of the thing that is most commonly asked of us. The areas, the circumference, the perimeter, distance, the Celsius temperature. But understand, everything that I highlighted there also is a variable in our equation. Does that make sense? And I think it gets overlooked a lot that when I ask you, let's just use the area of a triangle one, and I ask you to work with that formula, most people just do this, 1/2 BH. That's not the formula. Does that make sense? That's usually the part of the formula that you're working with to get the capital A, but there might be times where they give me, in my story problem, they tell me the area of my triangle. They tell me the base of my triangle. And my task then is to find out how tall that triangle is. What's the height of it? Does that make sense, everybody? So when you're working with formulas, do not neglect the variable that is by itself. That is a very important part of your formulas. And the reason I talk about that is because I use a lot of formulas in my other classes, okay? And I think that when I work with those students with formulas, and I ask them what's the perimeter of a rectangle, what's that formula, they say 2L plus 2W. They're kind of right, but it's got to be P equals 2L plus 2W. Okay, and I don't think that's been taught well enough in the past to realize that these things cannot just disappear. Okay, these capital letters are variables over here. All right. Tomorrow we'll pick up here, and we're gonna go into just doing example after example after example with these literal equations. I think they're a little bit more difficult than your normal equations because you're not getting a concrete value back. So we'll spend some time on that. Maybe use Desmos a little bit to check ourselves. No homework tonight.
I work.